going on at the centre here, and that's the feedback due to the central black hole. Let's move into it. This is zooming in. What we see, that's the black hole at the nucleus. It's bright because it's active. There are then these bubbles either side, and more bubbles like this. This is where the black hole has energized jets that come out, relativistic jets. I'm not going to describe them in any more detail. The energy comes from very close to the black hole, out to here through jets, and inflates stuff within the hot gas, making what we call bubbles. These bubbles are buoyant, and so we see this process is feeding energy out into the surrounding gas. If you now go same scale, look at the optical image of it, you can see the individual galaxies. This galaxy, there's clearly something interesting happening here, and this image is showing lots of excited emission from this central galaxy. The heat coming and energy coming out of this galaxy mechanically from the black hole is around 10 to the 12 times the luminosity of the sun, only it's coming out mechanically, and we think it's coming out through the jets and propagating further out as sound waves. I'll show that in a minute. So this is another image of the center. We can see more clearly what's going on. This is a pressure map, and the radio emission, that's the radio emission fitting into this middle bit here. And here we can see evidence for these sound waves, where we can see, I hope you can see, there are ripples going further out, where the energy is being fed from the center, the bubbling at the center, out to the rest of the cluster. We were very excited to discover these ripples about 10 years ago, and it looks like you can go from the center to the outside. The ratio of the size scale from the horizon of the black hole, which is where the energy is liberated, out to here, is a factor of 10 to the 10. So that's evidence, I think graphic evidence, that there is this feedback, energy is able to go further out. What's it do in other galaxies? This is one of the nearest quasars to us, called Markarian 231. You can see there's a cross on the center, very bright nucleus. That's because it's a quasar. And this is now a map showing velocity structure of the gas around it. And there are large velocities. It's going between minus 1500 to minus 300. Those velocities are indicating that there's gas flows which are much larger than the gas flows you'd expect from such a galaxy, which would just be a few hundred kilometers per second, and then negative, which indicates it's coming towards us. So the black hole is clearly doing something to the gas in that galaxy. Here's the press release picture of that kind of work, where all the quasar at the center is blasting all the stuff away. And it's probable that the growth of the black hole, which can then push the gas away, which also will switch the quasar off, is why these galaxies are essentially red and dead. What is the mechanism for doing it? One is the one I described with regard to the cluster of galaxies. It's happening through jets. Another mechanism is that it could be due to radiation pressure or winds. This is just demonstrating radiation pressure and winds. This happens to be Hale-Bopp, and that happens to be the Andromeda Galaxy. It's not responding to the radiation from the Andromeda Galaxy. Okay, the sun is over there. So solar radiation pressure acting on dust in the comet's halo is blasting it out, forming the tail there. That's basically the dust tail, which is due to radiation pressure. And ions within the halo of the comet are being streamed out by the solar wind, a wind from the sun. Quasars have both high radiation and high winds, and so both processes can sweep the gas out of a galaxy. And I and others have worked with the way in which you can get the energy, the radiation pressure, or the winds to push the gas out of the galaxy and basically switch everything off, and you end up, if you use radiation pressure, it's quite easy to get a relationship of 1 in 1,000 coming out of this. Therefore, what we think has happened, where this is just a schematic plot showing this is a logarithmic plot showing the number density of galaxies. This is using their luminosity versus their luminosity. It's a function that breaks and like that. Or if we look at the masses of halos, basically the halos, the dark matter halos that galaxies sit in, has a power law distribution. Therefore, you might expect that the baryons falling into the dark matter halos would lead to a power law distribution of galaxies, instead of which it looks like that. What's happened here, we think, is rather than them being up here, they've been switched off by this AGN feedback. It's the energy fed back by the black hole at the center of the galaxy. So, therefore, most galaxies, the universe will be much prettier and brighter if it were not for the black holes which are pushing the gas around. These galaxies would be a lot brighter than they actually currently are. So that's the major processes, and I'm just flagging there. I wrote a review all about this that's in the annual reviews of astronomy and astrophysics and published last year, if you want to check up and follow the references. Now I'm going to go to my last topic, talking a little bit about how the quasars actually work. How does this accretion take place right close to the black hole? What's going on? I've got a schematic here, which is the black hole, and this is the accretion disk. Material falling into the black hole is very likely to have angular momentum. Certainly it's likely to have enough angular momentum to swirl around the black hole. You don't expect it to fall in radially, and it's got to get rid of the angular momentum, and therefore it's got to have some viscosity. We think it's magnetic viscosity. We think this disk is a highly magnetized hot plasma, and angular momentum exchange, viscosity happens through magnetic fields, and so the matter goes in, the angular momentum is fed outwards, allowing the matter to get to the black hole. We have a differentially rotating magnetized plasma. That tends to lead to dynamo action, generates magnetic fields, which will then become buoyant and pop out of this disk, and they may reconnect above, forming a corona, like the solar corona, and that's what this star is meant to indicate. That's going to liberate energy through reconnection and accelerating particles. Those particles will radiate, they will inverse Compton scatter the thermal radiation from the disk and give rise to a power law of emission that comes to the observer. This is explaining facets of what we see. There's a direct power law of emission, plus there's black body emission from the disk. Just in terms of the differentially rotating magnetic fields, this is just a picture of the sun's surface in a particular waveband showing lots of magnetic activity. And this is an X-ray image or movie of the sun taken by a Japanese satellite, and you can see all the action above it. Now imagine that scaled up by a factor of 10 to the 12, and you've got an accretion disk around the black hole. If we look at the power law emission, it's often very variable. That's a length of about a day, and you can see extreme variability from this, and this emission is the power law emission that comes from the corona. But now the power law is irradiating the accretion disk, and it gives rise to backscattered X-rays and fluorescence from the disk, and we call that the reflection spectrum. It doesn't obey the simple laws of reflection, it's just a name for it, but this is just the sort of technique that is used in engineering and in physics, where you irradiate something from the outside. You irradiate it with X-rays, look at what comes back, and you can work out what it's made of. So we can work out what disk is made of, but more importantly, we can work out its velocity and its gravitational redshifts. Because the irradiating material is going to give a spectrum back looking like that, depending upon whether the intensity is sufficient to ionize it or not. And so we get spectral lines. If we've got a spectral line from accretion disk going around a hole, then this is just a little spectrum of it. Then if it was Newtonian physics, we'd have a double horned line. with special relativity, because the material is going up to half the speed of light, you'll get beaming aberration of light, so the blue horn is going to be brighter than the red horn. And then we're very close to the black hole, so we're going to have gravitational redshifts, and that means everything's shifted to the left, to lower energies, and when you add it all together, we end up with a skewed line profile like that. And so a non-spinning black hole, we predict the emission from a disk would look like that, and for a rapidly spinning Kerr black hole, we expect it to look like that. These wiggles are just numerical, so don't worry about them. But basically, how far down this goes measures the amount of gravitational redshift. And actually, as the black hole goes from being non-spinning to rapidly spinning, the innermost stable circular orbit of the disk around the black hole moves inwards, so we can measure that, use that to measure the spin of the black hole. What we've got is not one spectral line, but a whole reflection spectrum. But overall, we expect to get, when you blur it relativistically, you expect to get something like this black line. You expect a soft excess, a broad iron line, and a Compton hump, as we call it there. And recently, this is with the New Star satellite launched last year, we've been able to make a spectrum of an object exactly over this band. And when we take away the power law, it looks like this. There's the broad iron line, and there's this big Compton hump. Okay? And we can measure from the width of this iron line the spin of that black hole. That's another one showing a large gravitational redshift. And the point I was making about measuring spin is this is a non-spinning black hole. Due to GR, the disk will finish before the black hole, and then material just plunges inwards. Whereas if it's a rapidly spinning black hole, then the parts of the disk are filled, and so you get more energy out, and you also get a larger gravitational redshift. And this is just a census that Chris Reynolds has made of spin versus mass, and there seem to be quite a lot of objects with fairly high spins observed. Now, one last thing in this picture, which I wish to, this is the final bit I'm going to talk about, is one way of checking that this picture I'm giving you about reflection is correct, is if this corona varies intrinsically, you'd expect to see the variation first in the power law and only later through the reflection spectrum, because this light path is it's shorter than that light path, okay? So the difference between them we call reverberation, an echo, and using this source, 1H0707, we had a very long spectrum of it, long observation of it, where we saw the ion K line, the ion L line in it, and then looking at this part of the spectrum where the ion L line means it's dominated by reflection, and this bit in between before the ion K means it's dominated by the power law. What we can do is look at a light curve in this band and a light curve in that band, and look for time lags between the two by looking at the phase of the cross spectrum. We can then, as I say, check for time lags. When we do that, we find for rapid variations, which are on scales less than 15 minutes, we're seeing a lag of 30 seconds. This lag is such that the power law is changing, and then the reflection is changing 30 seconds later. So this is an object about 270 million light years away, 270 million light years away, and we're measuring a 30-second delay on these two paths. We can then go and look carefully at the whole spectrum of the time lags, including these time lags over here, which I could talk about but won't, down there. Those do not show any sort of ion K structure, they just keep climbing up. They look similar to lags that are seen in galactic sources, so I'm not going to talk about them, but when we look at those lags, we find the spectrum of the lag shows the ion K line indicating we're seeing reflection. So the high frequency lags in these objects have got the reflection spectrum, and so everything I think is fitting together. And this is just a comparison of two sources. This is the one I've already shown you, 1H0707, where it looks like the lag is over here. That's for that one. And this is another source. It's a very similar shape over onto that side. It's a different lag because we think it's a more massive black hole. And Barbara DeMarco has looked at a whole bunch of objects and found these lags, and there appears to be a correlation with mass of a black hole, and notice that these lags are comparable to just the light crossing time of just a few gravitational radii. So what I've been saying is we are in these observations measuring time lags from very close to the black hole. We're actually looking at what's going on as the material swirls down just a few gravitational radii from the black hole. To show a few theoretical plots that my colleagues have been doing, this is showing what we think might be the transfer function. If you were to have a flash of light above the accretion disk around the black hole and see what happens, this is now tilted at 45 degrees. The flash is at 10 gravitational radii. What happens in energy is, let's imagine the flash is occurring and the fluorescent line is at 6.4 keV, iron K. You'd expect to see something to start with happens when it touches the near side of the disk, then that's touching the far side of the disk, and then as it propagates further away, you end up getting the rest of this. Meanwhile, due to, again, gravitational time dilation, as the path of light goes closer to the black hole, you get this path coming down here. So if you project onto this axis, you get the broad line structure I've already shown you. To project that axis, you get a transfer function in time across there. And this is just showing you with iso delay surfaces, sort of trying to show what happens. First of all, this is now 60 degrees. The corona is just here, or the thing that's flashing is just there. First of all, you see it coming from that bit there, and then it expands and you see the other side and so forth, which is accounting for the shape of this structure. And my graduate student, Dan Wilkins, has done a beautiful colour picture of this with all the other lines you expect to see, but it's essentially the same thing. Of course, we don't expect the corona to be a point, so you've got to add together all these different parts. You can make up the transfer function for an extended object by just adding them all together. So just to conclude, talk a little bit about the future. What is the future of this work? The galactic center, well, I mentioned it when I was talking about this. There's a cloud of gas which may or may not have a star in the middle, which is falling into the galactic center. It's being seen moving there like one of those stars I showed you in that earlier image. It's probably getting there about now. It's not actually going to hit the galactic center itself. It's not going to hit the black hole, but there will be strong tidal forces on it, which is thought to strip gas from the gas cloud, and some of that may fall into this the black hole. So that's something to watch out for. And the other thing is there are people making use of radio telescopes on Earth and using them across the whole Earth, making the Event Horizon Telescope, which will be the size of the Earth, and with that looking for the shadow of the black hole, because the black hole is of course black, but material swirling around it should be bright, and so you can see hopefully an image which has a black part in the middle, which will be the image of the black hole. That will be very exciting. And we can also do that with M87. This is the 6 billion solar mass black hole I mentioned earlier. Look for the shadow image there, and as you probably all know, there's a group here in ASIAA which is hoping to do this, making use of a telescope they're going to put on the summit of Greenland. It turns out that the size of these images should be similar, but this is because the distance between us and the galactic center and us and M87, this thing is about 2,000 times further away, but the mass of the black hole here is about 2,000 times higher, so the angular scale of the black hole should be roughly the same. So that's going to be really very exciting. We know that this object also has got a jet coming out of it, a jet of relativistic plasma, and trying to understand and see where that jet is accelerated is going to be very important. So that's all of this work. I expect to give results not next year, but maybe in the next 5 to 10 years, we expect to get all of these answers in. With regard to AGN feedback, all of this, there are many new telescopes coming online, all of which are going to be looking at the AGN feedback. And in X-rays, which I'm involved in, Astro H, the next Japanese-US satellite, should be launched in 2 years' time, will give us lots of insight into what's going on. So my last slide, what I hope you take away with you is that supermassive black holes are common in the universe. They lie at the center of most galaxies. They appear to play a key role in the evolution of galaxies, terminating their growth. And their influence extends over a factor of 10 to the 10 in radius. What is a factor of 10 to the 10 in radius? It's roughly the ratio between this coin and the size of the Earth. Can you imagine something, this is, I know you're physicists, but and you're used to dealing with very small things, very large ranges, but something this small having an influence over something which is the size of the Earth, macroscopic objects. And I haven't talked about stellar mass black holes, but I could have done, and just to say that there are many stellar mass black holes in each galaxy. Thanks for your attention.
Thank you very much. Are there questions? You showed a picture of a sound wave, a ripple.
Yes.
And I want to ask that, what is the period of this sound wave and what kind of scale?
The period of it is around 10 million years, and the scale is around 30,000 light years. Okay? When we first discovered this, and the period of 10 million years, we did a press release on it, and it was calculated, not by me, alas, but by somebody else, that this corresponded to a B flat that was 54 octaves below middle C. And I ended up being, a couple of years later, I was in the Guinness Book of Records as having discovered the deepest note in the universe. I won't sing it for you now. Might take too long. But it's the only thing I've done that has deeply impressed my children.
It seems to me that the growth of black holes in galaxies still looks like a hypothesis. You showed some example of heating and ejecting, pushing things out. But mostly we see spiral galaxies a lot and then elliptic galaxies a lot.
Yeah.
Anything in between? Because do we have strong evidence that all black holes are actually growing?
No, of course, we only get a snapshot of the universe, but the best evidence that the black holes grew by accretion is the fact that it's called the Sultan argument, that if you add up all the light that you can see in the universe, which comes from accretion, and you can do that by looking at what's known as the X-ray background. So you can look in the X-ray band. It was discovered in the first rocket flight 51 years ago that there is a background radiation of X-rays everywhere. It's more intense in terms of more X-rays per square centimeter than the sun, the quiescent sun. Okay? We now think that is the sum total of all accretion sources out there. It's been resolved as being the sum of those. So therefore what you can do is work out the energy density. That's the number of ergs per cubic centimeter. I'm using it CGS units, sorry, but you can work out the energy density in radiation due to accretion above the Earth's atmosphere. Then you can use E equals mc squared with this factor of 0.1 in, and then you can work out the mass that must have accreted to do that. Therefore, you can get the mass of the black holes, the mass density of black holes in the universe, of course, smeared out. Okay? And you can do that by just taking the number density of galaxies locally, and then working out what their mass is, and then dividing by 1,000, and that will then give you the smooth mass density due to black holes. Okay? So that's a very good check between the two. I've forgotten to say there's one cosmological correction needed here, and that is the radiation coming from those distant objects is redshifted, so there's a 1 plus z factor goes on the left-hand side, but mass is not redshifted, so you don't need to do any more cosmology. It doesn't matter what your cosmology is, this equation is correct. Okay? And when you do that, you find the two things agree. We have no other explanation for the X-ray background, which does appear to come from all these sources. So the fact that two things agree is generally agreed by us, that this is evidence that the black holes grew by accretion. So that's our, I agree it's an indirect argument. I hope you were able to follow it, but it's an indirect argument as to why we think that's true.
My question in part was that if that is correct and you have a plot of distributions, shouldn't we see much more direct evidence? Look at different Z's, we see turning from
yes.
Spiral to elliptic and so on.
Well, yeah, the spiral galaxies are a bit of a problem here because the spiral galaxies still form stars. They're going to be more difficult to blow that gas out. Okay, but of course there's an enormous amount of work is going on and being done as a function of redshift of the development of elliptical galaxies. And what is seen is the most massive objects appear to switch off first. So elliptical galaxies, which you see at redshift 2, appear to sort of do their thing until redshift 1, and then, or even 1.5, and then stop evolving. So it looks like they are dead since around a redshift of 1 to 2. That's the elliptical galaxies. Whereas the lower mass galaxies continue to evolve longer. And I think we can work out why all of that's happened. Because what happens with the most massive objects is they maybe form their and grow their black holes first, and the black hole then switches them off. And there are, of course, there are many papers, many theories about all of this, and you can fit things together.
So you mentioned the G2 clouds,
Yes.
and you said some of them are going to be ripped apart and some of them are going to suck into the black holes. So do they have anything to do with the Penrose process of a curved black hole?
Well, we don't. First of all, I mean, of course, the black hole at the centre of our galaxy is probably spinning, so it's a curved black hole. But whether we don't know its spin. That's something which we hope to measure in the future. It will be very exciting if, in fact, the Penrose process were to operate. That is, if you don't know what the Penrose process is, look it up on Wikipedia. But of course, what is going on is by making collisions just right, you can tap the spin of the black hole. You may be able to tap the spin of the black hole using magnetic fields, and maybe jets will come out. So if in fact it switched a jet on, that might be, I know people would instantly write papers claiming it was due to the Penrose process. There would also be papers claiming it's not. So it is going to be very exciting when it does actually happen. It may also be a damp squib. You probably have all heard about how comets, a comet is going to occur later that year, and then it doesn't. Of course, the comet's still there, but predicting these things is very difficult. But an intriguing thing, if I can just take a minute to explain something, the black hole was 1 million times more active 100 years ago. How do we know that? Okay, and that is that there are molecular clouds either side of the center of our galaxy, which are 100 light years away, and those clouds are fluorescing in X-rays, giving K-alpha X-ray fluorescence. Okay, and you can see that X-ray fluorescence moving through the clouds. Okay, and the only explanation for it is that the black hole at the center caused the fluorescence by irradiating them, and you can work